Welcome back. We are talking about pulleys now, and we're still in rotational dynamics. Static equilibrium was where things were not accelerating tangentially or angularly. The net torque was zero, the net force was zero. Then we did some dynamics things where those were not necessarily in static equilibrium. There was some type of acceleration, whether it was tangential or angularly. Pulleys we're going to keep going with, and we've done some pulleys before. You've probably seen problems like this back first semester when we were doing dynamics. We used to say, oh, but you get to ignore the pulley, you get to assume that it's massless, or you get to assume that it's frictionless, that you don't have to worry about that. Now we're actually going to think about pulleys that have mass. So they have a moment of inertia, there's torque acting on it, and that's going to change our acceleration. It's getting more real life here. We've got a pulley. Pulleys are discs of a mass capital M, so that's 3 kilograms. The radius there is 1 meter. We're still going to say the string is massless. We don't have to do calculus in this class. If you did do calculus, you'd have to be thinking about how that mass is changing as time goes on. And then the mass little m here that's hanging is 2 kilograms, starts from rest, and it's only suspended from one string. And then as it's released, it falls down and the mass unwinds and spins. And we're supposed to draw a free body diagram for both of these masses. So little m here is going to have the force of gravity, which is little m times g, and then there's also a tension acting upwards on that. Not necessarily balanced, it's probably going to accelerate, so that mass times gravity, the force of gravity would be stronger there. On our big mass, on the pulley, it also has a capital Mg force of gravity acting on it. There must be some type of axle here, which means there's going to be a normal force, but the big force we're concerned with this one is the force of tension that's acting over here a distance of capital R, that radius away, and it's that tension that's going to cause a torque on that pulley mass. Our key strategy here is going to be down here. It says key strategy. We're going to find the sum of the torques for the pulley. So we're finding sum of those torques there for the pulley, and then we're going to find the sum of the forces for the hanging mass. And that really ends up being our strategy for the next 3 problems, this one and the next 2. You're going to do the sum of the torques for the pulley, and then every mass you have that's hanging, you're going to do a sum of the forces for that. So let's do that. Let's split this up. We're going to do sum of the torques first. So sum of the torques is equal to the moment of inertia times alpha, angular acceleration. Our radius here was capital R, and the force that was causing that torque was tension. If you look at, we do have other forces, the force of gravity, the normal force, but since those are acting at the axis of rotation, that distance is 0, provides no torque. The moment of inertia for a disk is 1/2 the mass, so that's capital M, times the distance, or times that radius squared. We still have angular acceleration in there. Take this a step further, and as we've done in previous problems, we are dealing with tangential acceleration of the system, so we're going to convert this like so. There's a squared in there, and all of these r's end up canceling out, and we don't have to worry about those. So we get that tension equals 1/2 times the mass of the pulley. Try to make that a capital M so you can see that, times A. And I'm going to circle this, and we're going to leave that there for a moment, and we're going to come back to it. Okay, so we're going to box this off because we're going to come back there. That was our idea with the pulley. Sum of the torques, we found the net torque. Actually, ultimately, we found tension. And we're going to use that here when we find the sum of the forces on that hanging mass. So let's look at the hanging mass now. Sum of the forces on the hanging mass are going to be equal to mass times acceleration. On that hanging mass, we have the force of gravity, and I'm going to make that positive because that as this rotates right here, it's going to go down. It's going to come down this way. And I know we had a talk about clockwise and counterclockwise, but way back in October, we talked about how it was more convenient for us, whatever direction the system was going in, to make that positive. So it's going to rotate this way, and we're going to make that positive. So the force of gravity is positive, force of tension is going to be negative, and that's equal to mass times acceleration. Okay, so you got mg minus the force of tension equals mass times acceleration. We found tension right here. Okay, so this is little m times gravity minus tension was 1/2 capital M times acceleration, and that's all equal to little mass times acceleration. Our goal here was to find the acceleration, so we're going to rearrange this equation, add this over to the other side. Mg equals little ma plus 1/2 mass of the pulley times the acceleration. And you can do all this out. You can do the algebra here. You end up with acceleration is equal to little mg all divided by little m plus 1/2 the mass of that pulley. Plug in some numbers here and you ultimately get, let's see, 2 times 10 all over 2 plus 1/2 of 3, and that ends up being 5.71 meters per second squared. Wow. That was a lot. That was a lot to do there. But remember the big strategy. We were looking at this pulley as it goes down, and we did it in 2 parts. Part of it was finding the sum of the torques on the pulley. The other part was finding the sum of the forces on the hanging mass. And that was only part C. We found the system's acceleration. The rest of this is mostly kinematics things. It says determine the angular speed of the pulley after 5 seconds. We can use this equation here, finding the angular velocity. We got initial angular velocity plus angular acceleration times time. The initial angular acceleration is, or the initial angular velocity is 0. I don't know my angular acceleration, but I do know my tangential acceleration. And I know that I can use this equation here, that tangential acceleration over the radius times time. So this is going to be 5.71 divided by my radius of 1 times my time of 5, and I get 28.6. What are the units for angular velocity? Radians per second. So that's just some more angular kinematics there. Part E, we actually haven't learned part E yet. It says determine the total kinetic energy for this system at 5 seconds. I'm still going to do it because we're going to learn it eventually, but you don't know how to do this yet, so don't feel overwhelmed. We're finding the total kinetic energy, and that's split between tangential kinetic energy or translational kinetic energy and rotational kinetic energy. We know this one, 1/2 mv squared. This is the mass of the block that's moving in a straight line. And then the other one is 1/2 the moment of inertia times the angular velocity squared. See the similarities there. Actually, I'm not going to go out and calculate all this, but if you really wanted to, you could. We haven't learned it yet, so I don't want to give away too much, but this is what I got. If you want to try that, go ahead and check that out. 1,431 joules. Okay. Again, haven't learned that, not necessary to know it right now, but it's kind of a taste of what's to come. Last up, it says determine the force exerted by the axle. If I scroll back up, on this pulley here, the pulley's rotating, it must be rotating about an axis. There is a normal force of the axis pushing that back up. That's got to be balanced with the force of gravity and the tension pulling on the pulley. These are balanced forces, so I know that normal force has to be balanced out with those forces there. We had an equation for tension earlier. If you scroll back up, our equation for tension right here was 1/2 big MA, so this is going to be plus 1/2 big MA. And let's see, what do we get? The big mass was 3, so this is 3 times 10 plus 1/2, 3 times the acceleration of 5.71. And I didn't do this right earlier, so let me get my calculator. 3 times 10 plus 0.5 times 3 times 5.71. And I get that this is about 33 newtons. Let's double check, see if I did that right. I did it wrong on my notes here, but I think I did it right on here. And that is that problem. Okay, a lot of this stuff, part F is balanced forces. That was a long time ago. Part D was angular rotational kinematics, so that's kind of new, but you guys should be good with that by now. Part E we haven't learned yet. You're not responsible for that. The big idea is part C, finding the sum of the torques with the pulley, doing the net force with the mass, and coming up with that tangential acceleration there. So that was number 46 for pulleys, and we're going to move on and keep doing some more. Here is our second pulley problem, and this one's a little bit more complicated, but we're following all the same general steps. It says we have an Atwood machine. That's just a name for this pulley system with two masses on each side. The pulley has mass this time, so that's what makes it different from dynamics way at the beginning of the year. Pulley has mass, 4 kilograms. We use a capital M for that. And a radius of capital R, which is 10 centimeters. Do not forget to change centimeters to meters. That's 0.1 meters. And two masses. M1, little m1 is 1 kilogram, and m2 is 2 kilograms, as shown. Part A is actually right below this. We're going to draw a free body diagram for each of these forces. So on this pulley here, on the pulley, we've got a few forces acting on it. There's the force of gravity. That's always on there. Force of gravity. There's an axle here supporting this, so that has a normal force going up. And then each of these strings that are attached to the masses below are going to have tension. So we're going to call this one force of tension 1. And then over here, this one is applying a force the other way, so this is force of tension 2. And as you can guess, we're doing torque. These are rotational things. The normal force and the force of gravity don't apply any torque, but tension 2 and tension 1 will apply torque. They are away from the axis of rotation, a distance of r, capital R, and it helps that they're both already perpendicular, so we don't have to find any components. Let's keep going down here. Draw a free body diagram for mass 1. These ones are pretty simple. This has the force of gravity. We'll call it M1G, and it has a tension force going up, force of tension 1. Similarly with M2, it's got M2G pulling it down, and then the force of tension 2 pulling that up. We're going to focus on the pulley and look at the net torque on the pulley, and then we're going to focus on each of the masses on their own and do a net force equation for those. Scroll back up here to part B, determine the acceleration of the system. Just as I said, we're looking at the torque, the net torque on the pulley, and we're looking at the net force on each of the masses. So let's do the net torque first, because that's what we did last time. We're going to follow that pattern. Sum of the torques here, it's the moment of inertia times angular acceleration. This time we have a couple of torques. I'm going to break my rule again, and you don't have to do it this way, but it really makes sense to me. If mass 2 is bigger, that's the 2 kilogram one, mass 2 is bigger, this is going to rotate this way, and it helps that this is counterclockwise, so I guess I'm not breaking my rule. But if this one was heavier, I would have it rotate that way. I'd say positive is whichever way it's going to rotate. So let's see, we got two torques acting on this. The first is the torque from the force of tension 2. So force of tension 2 is going to have a torque going this way, and then we're going to subtract the torque from the force of tension 1. And that's still equal to the moment of inertia. The moment of inertia for a disk is 1/2 big M r squared times the angular acceleration, which we're going to put as tangential acceleration over r. I'm taking shortcuts here because you've seen this on a previous problem. We add up the torques. In this case, we now have two torques. Moment of inertia right here, 1/2 mr squared. Angular acceleration is a over r. I shouldn't have to show you this. If you distribute out the r on this side, you can multiply that r over, you'd have 2r squared, so however you want to do it, but all of these r's end up canceling out. If you don't see that, you need to work through it. You need to understand the algebra that's occurring there. Simplified down now, we've got the force of tension 2 minus the force of tension 1 equals 1/2 times the mass of the pulley times that tangential acceleration. So we're going to block that off, and we're going to use this a little later when we're trying to solve for that acceleration. Let's look at the net force for each mass now. So for mass 1, we'll just say mass 1. The net force on mass 1 is going to be mass 1 times its acceleration. That's Newton's second law. And that's going to be equal to the force of tension 1 minus that force of gravity on mass 1. Kind of scroll down so you can see this. Mass 1, the tension's in the positive direction, the force of gravity's in the negative direction, because we're saying that going around that way, counterclockwise, is positive. And if we resolve this in terms of tension, we get the force of tension 1 is equal to mass 1 times its acceleration plus mass 1 times gravity. And I'm going to circle this as well because we're going to use that in a second. Do the same thing for mass 2. We get that mass 2 times acceleration, its net force is equal to, and in this case we have the force of gravity on this mass is positive, minus that tension. This is just like what we did back in the dynamics unit way back in first semester. And if I solve this for force of tension 2, we get force of tension 2 equals m2g minus m2a. I'm going to circle that. Whew, that's a lot. Section this off. Now we're going to plug each of these tensions back into our torque equation, have a whole lot of mess there, and then simplify and solve for A. So torque 2, or force of tension 2, that one was m2g minus m2a. I'm going to section that off. Minus tension 1, which was m1a plus m1g. And all of that was equal to 1/2 big M A. I'm going to kind of distribute out this negative here and do some simplification. M2g minus m2a minus m1a minus m1g equals 1/2 big M A. See if I can't get some of these things to the other side. So we get m2g minus m1g equals 1/2 big M A plus m2a plus m1a. I moved everything with the acceleration on one side, kept the other stuff on the other side. I can distribute an acceleration out, and I end up with acceleration equals to m2g minus m1g divided by 1/2 capital M plus m2 plus m1. Wow, that is a mess. Let's plug in some numbers here. If you didn't understand this algebraic thing here, I took out the acceleration, distributed that out or factored that out, and then divided by everything back to the other side. Let's plug in some numbers. M2 is 2, so this is 2 times 10 minus 1 times 10, all divided by 1/2. The mass of the pulley was 4 plus 2 plus 1. So is that what I had here? Let's double check on my calculator. Divided by, and I get a tangential acceleration of 2 meters per second squared. That is what I got earlier. Good deal. 2 meters per second squared. Looks a complicated mess. You're looking at the screen, or maybe you've written this down, and you're thinking, there's no way. Remember the strategy. We're solving for the net torque for the pulley, looking at the net torque for the pulley, solving so that we have the tension, or the tensions in this case, equals something related to the acceleration. Then we go to the net forces on each of the masses, solve for those tensions, we substitute in, and we solve for acceleration. In this case, we got 2 meters per second squared. Next up, we want to solve for the tension in the string attached to mass 2. Remember, for mass 2, up here above, we said that the tension in mass 2 is equal to m2g minus m2a. This was from solving for the net force on mass 2, right up there where I'm circling around here. So this is going to be mass, plug in some numbers. Sorry, that's 10 minus 1, 10. 2, so 10 minus 2 and we get 8 newtons of tension there. Good deal. Keep going. The pulley completes 3 revolutions. Determine the speed of mass 2. Alright, so something with rotational kinematics, but mass 2, as mass 2 falls on this side, it's not rotating. So how do we combine these two? Well, we're gonna do this equation. We're gonna do final velocity squared equals initial velocity squared plus 2 times the acceleration times that distance, and we're gonna try to solve for this final velocity. I know the acceleration from earlier, that was 2 meters per second squared, found that here. The initial velocity is 0, but I don't know that distance, or do I know that distance? If the pulley's doing 3 revolutions, I can say find x by doing the radius times that angular displacement. What is that angular displacement going to be? If we do this out, what was our radius? Radius was 0.1, so this is going to be 0.1, and that angular displacement is going to be the 3 revolutions times 2 pi. So angular displacement is going to be 3 revolutions times 2 pi, because there's 2 pi radians in each revolution. So if I do this out, I get that it's about 1.88 meters, and we're going to use that over here in this equation. So I end up with final velocity equals, the initial velocity was 0, so the square root of 2 times the acceleration of 2 times 1.88, and we get about, let's make sure I did this right, take the square root, that's what I forgot, about 2.74 meters per second. That is the final velocity. That's the velocity after that makes 3 revolutions. Last up is determine the force exerted by the scale. If you look at our free body diagram here for the pulley, the force of gravity is pulling it down. It's got these 2 tensions acting on it. The normal force is the force exerted by the axle. We want to find that normal force. The pulley, although it's angularly accelerating, isn't accelerating vertically, so those forces are balanced. So I can say, hey, the normal force is equal to force of gravity plus each of those tension forces that are also pulling it down. I found tension 2 up here, and that was 8 newtons. So really I need to find tension 1 first before I can solve these. So tension 1, what was that equal to? Tension 1 was mass 1 times acceleration plus mass 1 times the gravity. So mass 1 times acceleration plus mass 1 times the gravity. The mass of mass 1 was 1 kilogram, so this is 1 times 2 plus 1 times 10. That's going to be 12 newtons. And I also want to find the force of gravity here. So the force of gravity is going to be mass times gravity, or 4 times 10. And that's for the pulley, so that's 40 newtons. So let's add these up. We have 40 plus 12 plus 8. And that's going to be 12 and 8 is 24. So this is 60 newtons of force pushing up from that axle. All right, big problem again. This is balanced forces way back in October. This is kinematics with a little bit of rotational stuff in there from earlier, so you shouldn't have too much problem there. Again, dynamics back in October. It was this one. This was the big struggle, but it shouldn't be too difficult. Finding the sum of the torques for the pulley, and then finding the net force for each of the masses, doing some substitution, and solving for acceleration. Good work. This is our last pulley problem, and thank goodness, because this is exhausting. These are difficult problems. So I congratulate you for sticking with it, and let's finish this one up. Same idea with the pulley problem. We're dealing with pulleys that have mass, so there's a moment of inertia. That's going to affect the angular acceleration of the pulley, which ultimately affects the acceleration of the system. This one, we're taking it a little bit step further. We did a pulley with 1 mass, then we did a pulley with 2 masses hanging, the Atwood's machine. This one is a pulley on a table. We have a 20 kilogram mass that's located on a rough surface with kinetic friction. We're given that coefficient of friction there. That string is attached to a pulley which has mass, so there's going to be a moment of inertia. The mass is 2 kilograms, the radius is 20 centimeters, convert it to meters, 0.2 meters. The other end of the string has a 5 kilogram mass hanging from it that's going to be pulling that down. We need to draw a free body diagram for the pulley in each of the masses. So look at this picture, kind of visualize this. I'm going to scroll down. First we have this mass. Okay, we have the tension, which I'm going to call the force of tension 1, because we need to have names for those. So force of tension 1 acting here. There's another force of tension, the force of tension 2 that's acting up here, right? You see that? 5 kilogram, which we're calling mass 1, and the 20 kilogram, which we're calling mass 2. We also have the force of gravity acting on this. That's always there. And when there's a normal force, there's got to be something to hold the axle up, but it's not just vertical this time. The previous times it was just vertical because it had to counteract all those downwards forces of tension and gravity. But since we also have a tension pulling in the negative x direction there's got to be a normal force acting this way. Okay, and that looks a little confusing, but I think you can handle that. On the 5 kilogram mass, we have m1g, the force of gravity, acting down on that, and the force of tension 1 acting up. On the 20 kilogram, it has also the mass of mass 2 times gravity, so its force of gravity. There's a normal force acting up because it's on a surface. There is the tension, which we're calling the force of tension 2, and then there's also friction. It said kinetic friction, so there's force of kinetic friction acting this way. That's a perfectly negative x. So this has a lot of forces acting on it. Pulley's got a couple tensions. Those are going to cause torque. Also has a normal and a force of gravity. No torque on those ones because the distance from the axis of rotation for them is 0. The first mass, mass 1, the 5 kilograms, just tension and the force of gravity, and the 20 kilogram one has a few forces acting on it. Big question, here it comes. Determine the acceleration for the system. Same strategy as last time. You're overwhelmed already, but same strategy. Sum of the torques on the pulley, then we're going to look at the net force on each of the masses. So let's start out with those sum of those torques. The sum of the torques is going to be equal to the moment of inertia times angular acceleration. The sum of these torques, it's going to be R, and I'm going to switch this up a bit. I'm going to call this direction positive because that's the direction it's going to go in. And I know that's breaking my rule of clockwise, counterclockwise, but I think it'll be simpler in the end, and I'm allowed to do that. Okay, so this is going to be times the force of tension 1 minus the torque from the force of tension 2. The moment of inertia for a disc, only for a disc and a pulley, is 1/2 the mass of that pulley times that distance squared. And then angular acceleration, we want that in terms of tangential acceleration. We've done that plenty of times. I'm doing 3 or 4 steps all in one just to simplify for us. Okay, we know that these radiuses are going to cancel out then. And what we'll end up with is that the force of tension 1 minus the force of tension 2 equals 1/2 mass of the pulley times the acceleration. Pause. Okay, we're going to pause this, I'm going to circle this, and we're going to come back to it. Next up, we're going to look at the sum of the forces for mass 1. So that was the sum of the torques for the pulley. Here are the sum of the forces for mass 1. Okay, mass 1 times acceleration, that's what the net force is. That's going to be equal to the force of gravity, which we're saying is positive because that's the way it's moving, minus that force of tension 1. And I'm going to rearrange this in terms of the force of tension. Okay, so this is mass 1 times gravity minus the net force, and I'm going to circle that, and we're going to come back to it. Same thing for mass 2. Mass 2, we have its net force is going to be equal to the force of tension 2, which is pulling it, minus the force of kinetic friction. I'm going to do a little skipping around here. So this is force of tension 2. Force of friction is the coefficient of kinetic friction times the normal force. The normal force is balanced out with the force of gravity in this case because it's not accelerating vertically. So this is going to be minus the coefficient of kinetic friction times the normal force, which is balanced with the force of gravity. So mass 2 times gravity. If you don't remember that, Go back to dynamics last semester and see if you can figure that out. Write this in terms of force at tension 2. So you get mass 2 times acceleration plus coefficient of kinetic friction times mass 2 times gravity. I'm going to circle this. Okay. We want to solve for acceleration. We have all these equations with acceleration in it. So we're going to take these two tensions and we're going to substitute it in here. I'm going to scroll down. I'm hoping I have enough room here. So we're going to bring this down and I'm going to substitute all of these in all at once. Okay. M1G minus M1A. Let's put that in parentheses. Minus force of tension 2, M2A, plus coefficient of kinetic friction, mass 2 times gravity. All of that equals 1/2 MA. For sake of space and redundancy, I'm only going to explain this to you and then show you how to solve for A. Notice this has an A, this has an A, this has an A. Those are the acceleration. That's what we're looking for. You need to distribute this negative sign through, move everything with an acceleration over to one side, and then ultimately divide by things to get acceleration alone. And I've done that here, and I ended up with this. M1 plus coefficient of kinetic friction. Sorry, this is a lot to write out. Big M, that's the mass of the pulley, plus M1 plus M2. If you plug in all these numbers, you're going to get your tangential acceleration of the system. Again, I know I jumped through a bunch of algebra here, but I'm thinking from the previous problem, if you got that, you should be able to do this. And I got 3.46 meters per second squared. That was our acceleration. I need to hold you accountable for the algebra. You need to be able to do that. I showed you the steps on the last one. This one's not a whole lot different. You should be able to do those. What I really want you to know is that we found the sum of the torques for the pulley and the sum of the forces for each mass, and we combine those through substitution and solve for the acceleration. Okay, those were the strategies. That was the big step. Let's go on and finish out the problem. This one says determine the tension in the string with the 5 kilogram mass. Up here, if you see, we solved for tension right here, and so we can bring that down and solve for that again. Force of tension 1 equal to mass 1 times gravity minus mass 1 times its acceleration. We now know that acceleration, so this is an easy calculation for us. 3.46. There's probably a little rounding here, but I get 32.7 newtons, so that would be tension 1. That's a dynamics thing. Net force, you guys know how to do that. Determine the tension in the string attached to the 20 kilogram mass. We solve for tension 2 above, so I'm just going to bring that equation down. And then I'm going to plug in all these numbers. This is back from an old unit, so this should be good review for you guys, and I get about 29.2 newtons. Good deal. Back in the old days, I remember when we did these problems and we found the tension, and if you found the tension in this cable here, it was going to be equal to that tension in this cable here, and that's no longer the case. Because we have a pulley that has mass, it has a moment of inertia, it has angular acceleration, it's going to affect the tangential acceleration, and those tensions can now be different. And I remember foreshadowing that and us being overwhelmed by it then. And now you guys have done these 3 problems, you've written them out. I expect that you can probably do it yourself, maybe by looking at the notes, and from there you're going to be able to do it on your own without having to look at your notes. Remember, sum of the torques for the pulley, sum of the forces for each of the masses, substituting and combining those, solving for acceleration. And the rest is review, either from this unit in rotational kinematics, old kinematics, or old dynamics, and you guys should be able to do this. You're pros. Good work. Thanks a lot.